Imagine you're building a table of students. Each row is meant to stand for one real person, one identity the system can always find again. But look at the roll numbers. Two different students both carry 101. Now, if I ask for student 101, which one do I get? The identity has broken. So a table needs two guarantees: a reliable way to point at exactly one row, and a reliable way to link rows across tables without ever pointing at nothing. Those two jobs are done by keys, and by the rules we call constraints. Here is a clean version of that table. Every roll number is now different, and every email is different too. Names and ages, though, are allowed to repeat. Notice to students share the age 20. A super key is any set of columns whose values are never repeated across two rows, so it always singles out one row. Roll number alone does that job, but name on its own is not a super key. Two different students can easily share the same name. Imagine a second Ravi walking in. The moment a value repeats, it can no longer single out one row. Same story for age. Now the quirk. If roll number alone is unique, then roll number together with name is unique as well. The extra column cannot hurt. So a super key is allowed to carry passengers it does not really need. Among all those super keys, we want the lean ones, the ones with no wasted columns. A candidate key is a minimal super key. It is unique, and you can't throw away a single column and keep that uniqueness. Roll number on its own is unique, and it has nothing left to drop. So it's a candidate key. Email on its own is unique too. This table has two candidate keys, standing perfectly equal. But roll number plus name is not a candidate key. It is unique, yes, but drop the name and roll number is still unique. It failed the minimal test. That is the single most common slip. A super key with extras is not a candidate key. With two equally good candidate keys, the designer simply picks one to be the official identifier. That chosen one is the primary key. Here, roll number. We mark it, and by convention, it can never be empty. Email is still a candidate key, just not the chosen one. So we call it an alternate key. Same power to identify a row, simply not wearing the crown. Sometimes, no single column can be the key. Take an enrollment table, recording which student takes which course. One student takes many courses, and one course holds many students. So roll number alone repeats. Student 101 appears twice, and course ID alone repeats. Course C's 101 appears twice. Neither column can identify a row by itself, but the pair, taken together, is unique. A given student appears with a given course exactly once. A key built from more than one column is a composite key. Here the primary key is roll number and course ID together. One caution to hold on to. It is the whole combination that must be unique, not each column on its own. Composite means together. Now the reason keys truly matter. Linking tables. On the left, students keyed by roll number. On the right, enrollments, each one belonging to a student. The roll number column inside enrollment is not the enrollment's own identity. It is a pointer. It names which student this row belongs to by referencing the student table's primary key. A column that points at another table's key, like this, is a foreign key. Say it out loud. Enrollment.roll number references student.roll number. The foreign key on one side must line up with a primary key on the other. And just like a primary key, a foreign key can be composite. If a table is identified by a pair of columns, another table points back at it with the matching pair together. The whole pair travels as one link. Here is the rule that keeps those links honest. Referential integrity. Every foreign key value must match a real primary key on the other side, or be left empty. This first enrollment points at student 101, who exists. Valid. Now watch what integrity forbids. Someone tries to insert an enrollment for student 103. We go looking in the student table, and there is no 103 anywhere. No parent row means this would be an orphan. a pointer to nothing. The database refuses the insert. That is referential integrity doing its job. The same rule bites from the other direction. Suppose we try to delete student 101 while an enrollment still points to them. Delete the parent, and that child row is suddenly an orphan too. So a delete needs a declared rule. On delete restrict simply blocks it. You must remove the enrollments first. On delete cascade goes further. It deletes the child rows along with the parent in one clean sweep. Keys are one family of a bigger idea. Constraints, the standing rules a row must obey before the database will accept it. Let's meet the everyday ones and watch each one reject a row that breaks it. Not null says a column can never be empty. Try to add a student with no name and it is rejected. Unique says no to rows may share this value. A second row with an email we already have is rejected, though unique usually tolerates a single empty entry. Primary key is the strict pair, unique and not null at once. A roll number of empty fails on both counts, so it is rejected. Foreign key is referential integrity again. A roll number of 103 with no matching parent is rejected. Check tests any condition you write. Demand age at least 0, and an age of -3 is rejected. And default is the friendly one. Leave a grade out, and it quietly fills in a sensible value instead of failing. Sometimes the keys are not obvious from the columns. They are hidden in the dependencies between them. Here the rules say A determines B, C determines D, and B and C together determine A. Let's find every candidate key. Take the closure of B and C. Everything they force to be determined. Start with B and C themselves. B and C together give A. Now A gives B, already there, and C gives D. We have reached all 4 columns, so B and C is a super key. Is it minimal? B alone closes to just B. C alone closes to C and D. Neither smaller piece reaches everything, so nothing can be dropped. B and C is a candidate key. There is a second one hiding, closer and C. A gives B, so we have A, B, C. Then C gives D, all 4 again. And its halves, A alone and C alone, each fall short. So A and C is a candidate key too. So R has exactly 2 candidate keys, A to C and B to C. Notice C sits in both. It appears on no right-hand side, so nothing can ever derive it, and every key must carry it. Your turn. Here is a table of books. The ISBN is unique for every book. Titles and authors could repeat. Pause the video and answer 2 things. What is the primary key? And is ISBN together with title a candidate key? Here is the answer. Since ISBN alone is unique, it is a minimal super key. So the primary key is ISBN, all by itself. And ISBN with title? It is unique because it contains ISBN. So it is a super key. But drop the title and ISBN alone is still unique. It is not minimal. So it is a super key, not a candidate key. That is the trap. And you caught it. Trap 1. And the big one. Minimality. A super key carrying spare columns is not a candidate key. Before you call anything a candidate key, remove each column in turn and ask, is what's left still unique? If yes, the one you removed was baggage and you did not have a candidate key. Trap 2. A primary key value can never be null. That is, entity integrity. An empty identifier identifies nothing. And notice the asymmetry. A unique column will usually tolerate a single empty value, but a primary key allows none at all. Trap 3. Foreign keys are allowed to be null. A null foreign key just means no link yet. Only the non-empty values must match a real key. Trap 4. A foreign key must reference a primary or unique key, never an ordinary column, and any value it holds must actually exist over there, or be null. Point it at a non-unique column, and the phrase one specific row loses all meaning. Let's lock it all in. The hierarchy runs from super key, down to candidate key, which is minimal, down to the one primary key you choose. The rest are alternate keys. A foreign key is a column pointing at another table's primary key, the thread that stitches your tables together. Entity integrity keeps each identity real. A primary key can never be empty and never repeats. And referential integrity is the promise that every such thread lands on a real row or dangles as null on purpose. Keep these four ideas straight, and keys will never trip you up.